Hey everyone, welcome to my channel. If you are interested in speaker design and improving sound quality, subscribe and join us. Today, we are going to design a 3D model of a folded horn speaker in the shortest possible time. This is the new version of the Excel file designed in the previous tutorials. You can download it via the link in the description. It includes 2 photos to show the required dimensions. The input data is based on these figures and the specifications of our desired driver. All the required links to software programs are available in the description. In this tutorial, all the horn parts will be completed and the horn performance will be analyzed. Don't worry about too many cells. You need a few of them. If you remember, we created an Akabak template. If you haven't watched these videos, their links are in the description and above. Today's work is not possible without creating a template. Watch them and create your own Akabak template. Enter the specifications of the driver you want. The black line is the desired cutting distance. You can put the green line on the black line or change it a little. Do not place it too close to the throat or away from the black line. If this cell turns red, it means that the distance is out of range. This cell shows the black line position. Enter the same value in this cell. We are done with this part. Click on the software worksheet. Set the smooth factor at 10. After that, select the horn nodes. Copy and paste them into the Akabak horn nodes. The horn points are visible now. Now do the same for all nodes. We actually create 3D points and then connect them to create a 3D shape of the folded horn speaker. This allows us to create the shape directly in Akabak without the need for additional software. The enclosure nodes. All you need is to copy and paste. As I said, you only need to make a template once, and all the steps in this tutorial are the same for all folded horns that will simulate in the near future. Now, it's time to connect the points and make the shape. On the BEM tab, start with baffle. Copy these point connectors and paste them into their related sections. Baffle to baffle, horn to horn, and so on. First, click on New button, then Delete to allow us to paste the copied numbers. A very important thing is to select the right nodes for the elements. Since we selected the baffle elements, we need to connect them to the baffle points. The baffle shape is created as simply as you can see. The horn consists of 2 parts. Copy its related values. The reason why we divide the horn and the enclosure into 2 parts is to determine damping for a small part of them, not the whole. Damping the whole walls of the horn and the enclosure usually kills all the transmitted sound through the horn. This Excel file has been created based on the set information about hyperbolic horns. The 2 parts of the horn are visible now, the yellow for damping and the gray for its hard walls. Pay attention to the left section. In every step, I select a new component to make its 3D shape. As you can see, the shapes are created without spending much time. So far, the horn and the enclosure have been completed. The green area is the damped section of the enclosure. As you know, Int 1 connects the enclosure to the horn. Int 2 connects the hole to the outer space. After doing all, we must enter the driver position for the rear and front cones. On the Position tab, type these coordinates points. Make the front cone visible and do the same for it. All the parts are complete and everything is ready to perform a software calculation. Push this button and wait till the end of the calculation. The calculation speed depends on your PC performance and mesh size. Drag the created files into VAX Viewer. The resulting response contains some peaks and nulls. The first tip is to eliminate them with a damped enclosure. Before it, for better evaluation and comparison, import the response into REW software. Only make a text file and save the response in it. Then drag it into REW. Select the wall impedance of the enclosure to create a damped box. For now, just enter a damping value regardless of the damping material. If you want to make the horn in reality, you can try some materials such as acoustic foams, rock wool, etc. Enter 0.08 or any values bigger than 0. Note that these green lights are an indicator to show if all the steps were performed correctly. They turn red for errors. This is the response after enclosure damping. The damping box did not effectively eliminate the fluctuations. It kills the bass, and the higher the enclosure damping, the more bass it kills. Make the enclosure walls rigid by selecting Newman walls. Then try to dampen the horn. The damped horn response is ready to drag into REW. After running the calculation button and importing into REW, comparing the graphs shows the damped horn works better than the damped enclosure. Of course, the damped enclosure may work for the other cases. The first one is the response without damping. The second is the damped enclosure. And the third is the damped horn. I leave this response as it stands. If you remember, we put a ground connection here. We want to get the driver's response, not including the horn effect. Connect the horn to the ground, which means to bypass the horn effect. After that, push the run button again. You can also see the horn response by bypassing the front driver. As you know, manufacturers obtain the driver response on an infinite baffle. Infinite baffle dimensions are really big, and the low frequencies are not reduced for a mounted speaker on it. The front cone on a narrow baffle reduces the wide frequency range due to the baffle loss. folded horn compensates for the baffle loss. It is shown clearly in these figures. Bypass the front driver to see the horn response separately. Now save it, then drag it into REW. The whole response is the sum of the horn and the direct driver. Don't forget to like and subscribe. Wait for the new exciting videos.